Hey everybody. Today, you can see the title on the screen. What we're going to work our way through are Exponential Functions 2. So what I want to specifically do is address, maybe some of the quirkier situations that you could be asked to deal with or encounter when dealing with exponential functions. The assumption made coming into this video is that you are very comfortable sketching an exponential function and understanding the properties of it. So if we're not quite there yet, then hop back and work your way through sketching. Otherwise, let's jump in and see some of these quirkier type problems. Here we go. Okay, what you see on the screen is some examples from our practice. And I want to focus in on the problem for 13a. That is, for you to go through, and I'll change the wording a little bit, not to specifically ask about graphing it, but instead sketching it. So I would like you to go ahead and sketch that function. Then what we're going to deal with is we're going to deal with part B, and then specifically I want to jump in to part 1 of B. Describe how the graph in part A would change for each of those functions below. So I want to deal specifically, how would the function above change if it were now to become y equals 2 times 5 to the exponent x plus 1. That's what we're going to deal with. So a couple things that I want to maybe walk through for how we can work with this problem and maybe even intentionally make a mistake on the problem so that we can understand how we can deal with it. So I'm going to change the problem a little bit for us. Rather than go and sketch the solution to A first, what I'd like you to do is to try B part 1. So I want you to take a moment and try to consider, how would the graph in part A, what I've circled in purple, change to become the graph that I've circled in blue? I want your statement to be a description that deals with transformations. So if I had to reword the question, how would you transform the graph in A to arrive at the graph in B? Okay, give it a shot. I want you to pause the video now. Go ahead. Okay, we're back. So if I were to walk through what I think would have been the most common mistake, is that I hope that we can see that the 2's out in front are the same, the 1's at the end are the same, that really what we had to consider when trying to bounce back and forth between the two functions is, well, this base 3 became a base 5. Okay. So I would have a lot of people recognize that 5 to the x is going to be steeper than 3 to the x as a function, and therefore maybe there's a vertical stretch by a certain factor. Okay, I want to make sure that we are good, that we do not make this mistake. I would have expected to see a lot of people write that it was a vertical stretch by a factor of, and then when you consider how to change a 3 into a 5, I would have had a bunch of people that would have said by a factor of 5/3. Okay, that's incorrect. And I want to make sure we understand why. If I was to go and write out what the blue transformation was that I just bulleted, then we should recognize that to go through and vertically stretch a function means to multiply the outside of the function by that value. And maybe you can see your mistake when you see it that way. That is, the only way that that base of 3 becomes a base of 5 is if you were able to multiply those two together. And we should be good that you cannot do that because you all passed grade 6, which means you know that you would have to do the exponent operation first before multiplying. You just broke bedmass. So I hope that we can recognize that a vertical stretch is not going to be the way that we can transform that function because it's exponential. So I could put a big cross through that, or I'm just going to erase it and make sure that we don't consider it. Okay, to make sure we don't get lost in all of that notation, I'm just going to delete all those things I circled so we can see the functions a little clearer. Yes, my graph in part 1, which I'll call my blue function, is steeper than my graph in part A, which I'll call my red function. But that's not the only way that we can get there. That is by doing a vertical stretch. I'm hoping that we could also see that we could deal with that as a horizontal stretch. Now, if we want to get really, really particular at this moment, I'm hoping we're good that we could have a horizontal stretch. And I'm going to skip some of the notation just for some speed, but we need to know that that factor has to be less than 1. If I vertically stretch a function by a factor less than 1, then this blue point, oops, sorry, I just need to do that in red. This red point would get stretched to the location of the blue point. And if I did that to all of my points, my graph would appear steeper. Something like that. So we should be looking for a horizontal stretch factor to be able to change that graph. Well, how do we horizontally stretch something? That means that we need to stretch it based on the inside of the function, and we stretch it by multiplying. So really what you are looking at is for some generic exponential function, let's call it b to the exponent x, you now need to multiply that by something out in front of that x. Let me just call it star. Okay, how do we figure out the value of star? Okay, I want to stumble my way through this a little bit so we can see how to build it. And then I'll talk about a shortcut. So let's build it first. Really what you see then is that if you could take the blue function and write it similar to the red, that is, you're trying to figure out how could you write a 5 as your base as a 3. Well, if you could figure out how to write a 5 as a 3, then you could just look and see what else is different about the function, and you could interpret that difference as a transformation. So what you're really looking to see then, if I get rid of those circles, how could I write 5 as 3 to some exponent? Now, I want to make sure that we don't get too confused with the x at times. And if we generically use an x, then we may look back at the original function and think that those x's are the same. They are not. So, my advice to you would be, use a different variable. We'll call that a. If I could figure out how to write 5 as a power base 3, then I could change that to a power. And since I would be changing 5 into a power, then everything is an exponent, which means I'm not breaking bedmass. Okay, let's see what that looks like in practice. Okay, how could I write 5 as 3 to some exponent? Well, you guys take a look at that. You see your variables, your a, it's up in your exponent. You got to get it out. That means you need a power equal to a power base the same. You cannot write 5 as a 3 as a base easily. So maybe we default then and say, okay, I'm going to take the log of both sides. That is going to allow me to bring that exponent out in front of my log. Now I could divide out my log 3. And I'm just going to slide that up on the screen a little bit. That would allow me to combine that back into one log using my properties of logs. Nice. What I just found out was that that a value could be log 5 from base 3, and that gives me the exponent I would put on 3 that makes that equal to 5. Okay, I want to stop you for a second because you might be able to see the shortcut. I want to remind you that back in our last unit, we talked about a certain property. That property being, if you have a power with a log in the exponent, and the base of your log is the same as the base of your power, then that expression equals the result of your log. We went through and we proved it last unit. You are free to use that property now. You might be able to see how we could shortcut our solution. So using that purple, I am now going to go directly from the green straight down using that property. If I want to figure out how do I write 5 as 3 to some exponent, well, I can put a log in that exponent, make sure that that log has the same base as my power, and it would have to equal my result. If you guys look at that green now, you can notice, hey, left side and right side are both equal to 5. Okay, why is that helpful? Well, it's because if I go back up to my blue function, my blue function being 2 times 5 to the x plus 1, I can now replace my 5 with 3 to the exponent log 5 from base 3. So if I do that, replace my 5 with 3 to the exponent log 5 from base 3, you'll notice I'm starting to change this into something that looks like the red function. Now both of those are powers base 3. I can now compare the difference, interpret it as a transformation. Okay, look inside. You have a power all raised to the exponent x. Well, if I have a power raised to another exponent, then I multiply those exponents. I am going to write that as x log 5 from base 3 so that I don't require brackets and I have no confusion over whether that x is inside the log or not. Okay, take a look at my red starred function at the very beginning and now my red starred function at the end. All I have to do is interpret my difference. So what is different about both of those equations? Well, if you take a peek, we have this times by log 5 from base 3 in my exponent. Okay, we should be good as to how to interpret multiplication in the exponent as a transformation. So if you had to describe that change, you should now be able to say that that is a horizontal, because we're on the inside of the exponent, stretch, because we're attached by multiply, so that gets a little confirmation for what we talked about earlier. You could then say by a factor of, and then we have to remember that when we're on the inside of the function, we've got our opposite operation. So in this case, I'm going to have by a factor of 1 over log 5 from base 3. Okay, if you go to check your solution to that, that is not going to be what you see. Because, and I'm just going to circle it, that expression that I just circled is actually unsimplified. We can simplify it further. So I'm going to go back to one of those properties we addressed last unit, that you can move a log across a fraction line. And if you move the log across its fraction line, you interchange your base and your result. So rather than writing 1 over, and I'm going to just get rid of that statement, I could have instead written that as log 3 from base 5. And there we go. Okay, as you're working your way through and you can see that whole screen now, we should be able to recognize that is something that you have never been asked to do before. Interpret how to transform a function when it's like a different function. One a power base 3, the other one a power base 5. But we now have the ability to change the base of our function in order to interpret it as a transformation. Nice. That is super helpful as we move forward. but absolutely a stumper for today. Okay, I'm going to throw another stumper at you, but I don't think this one is difficult for the same reason. So what I want to do now is I want to jump into another problem. I want you to take a look at the screen. We go right back to our original 4 problems. And what I want to focus in on now is problem 3. I want you to try to describe how the graph in part A, and I'll stay with the same colors, the red one that's circled versus the blue one that's circled. So how is the red function changed to arrive at the blue? Same thing as what we did previously. What I want you to do is I want you to try it without graphing. See what you can come up with. And then we'll walk our way through and see how we could actually deal with that in terms of a transformation. Okay, I want you to give it a shot. Pause the video now. Okay, we're back. So you guys take a peek at that, and the common answer I would expect to get is that, and I'm just going to circle here, in your blue equation, you have a negative out in front. Your red equation, you do not. So if we interpret that negative out in front as a reflection in the x-axis, I would have a number of people that would tell me, reflect in the x-axis, and we are good. We then take a look at the end, because you see the 2 and the base 3 are the same, that really the only other difference is a 1 became a 5. And so we then would say that we would shift up 4 units, and we're good. Okay. I need us to understand that the orange is good. The green is incorrect. Now, it seems terribly logical what we just went through. But what I want to go through now is to incorporate the graph portion of this. So what I'm going to ask you to do, create a quick sketch of what the graph in 13A looks like. So if I get rid of all of my circles, I want you to create a sketch of your red function. And then what we're going to do is we're going to create a sketch of the blue, and we'll see how things match up. Okay? I want you to create a sketch of the red. Pause the video now. Okay, we're back. So what I'm going to do is I'm going to assume that that orange and green you guys are good with. Maybe not as to why the green was incorrect, but that you've got it down on your page. So I'm going to save that space a little bit, and I'm going to shrink this down, and I'm going to produce a sketch for the red. We should be okay that we are going to have a horizontal asymptote, and I'm doing this really sloppy. I'm not doing this as a formal sketch. This is you in a problem-solving situation. So you see your horizontal asymptote at y equals 1. You know you have an increasing graph, vertically stretched by a factor of 2, shifted up 1. So I'm going to get something that then gets steep. If you want to take a look at some of your key points, you'll notice that your new y-intercept should be at 3. Okay, there is a quick and functional sketch for the red function. Now, we're going to produce the blue. So my blue graph should have a horizontal asymptote at y equals 5. We can see that it was a graph that was 3 to the x, so rising, but because of the reflection in the x-axis, it's now going to be decreasing, it's going to be falling. And if I was to calculate my y-intercept to try to match up with the red, I would sub in an x equals 0, and I actually find that I have the same y-intercept. So if I was to put on my sketch for that one, then I'm going to get something that looks like that for my blue function. There's my graph. So what does question 13b, part 3 really say? It says, what transformations would you do to the red to turn it into the blue? I hope that we can see with the picture that the reflection in the x-axis is still what's needed. We need to change our graph from an increasing function to a decreasing function. But maybe we can't see why shifting it up 4 won't work. So graphically, what I'm going to do is I'm going to deal with a new sketch for each transformation. So if we said that we need to reflect in the x-axis, then what I'm going to do is I'm going to take my red graph and I'm going to do the orange to it. I'm going to reflect it in the x-axis and I'm going to see the outcome. Okay, if I take my horizontal asymptote at y equals 1 and I reflect it in the x-axis, then I'm going to have a horizontal asymptote at y equals -1. Some of you might be able to see right now why I can't shift that up 4 to get to my blue graph. Okay, but say we keep going on. My curve is above that asymptote in my red, so it's going to be below. My y-intercept of 3 on my red becomes a y-intercept of -3 on its reflection. And if I was to now sketch it, I get that orange. Okay. Now, what I want you to do, now that my orange is the correct shape as my blue, shift it. So I want you to take a moment right now. You don't need to pause it. We should be able to do this live. And figure out what would you shift your orange graph to get to the blue. Okay, there's 2 ways that we can look at it. You can look at the asymptotes, which may have been the first way, and you'll notice for you to get to y equals -1, shifted up to y equals 5, you had to go up 6 units. Now, you may also look at your y-intercepts and say, but to go from a y-intercept of -3 up to a y-intercept of 3, you had to go up 6 units. And you guys might actually see why the correct answer to this one would then be to shift up 6 units and not 4. Okay, this one is different for you. But the reason why it's different is because this is probably one of the first times where you've ever had to deal with the transformations to an already transformed graph. In particular, what caused the wrinkle? The fact that my base function was shifted vertically. As soon as I shifted it vertically, I took the asymptote off of your x-axis. So now when I reflected it, my asymptote also reflected. Like normally my asymptote's just on the x-axis, so if I reflect it, it doesn't move. Now it moved. There's the key difference. Okay, drawing sketches for that could be time consuming. You may look at it and go like, okay, but is there a way I can deal with that where I don't have to draw a picture? Yes. What I'm going to do is just look at that graph portion, but solely algebraically. And what I'm going to do is I'm going to take my original red graph and I'm going to algebraically do my transformations. And you guys will see one big difference. Okay, I'm going to deal with the orange. So I'm going to reflect my graph in the x-axis. If you think that this orange equation is you reflecting that in the x-axis, there's our mistake. And some of us, just because of our background, might have in our mind that, well, to reflect a graph in the x-axis, you just put a negative out in front. And that's incorrect. Really what it is you have to multiply the outside of your function by -1. Right? Outside the function is vertical. That's what gets it across the x-axis. Multiply by -1. Multiply is what gives us our reflection. that when you look at that orange equation, that's incorrect because you didn't multiply the whole function, the outside of the function. You just multiplied the first term. Okay, this would be a correct interpretation of reflecting in the x-axis, multiplying the outside of the function by -1. What you'll notice, you got to multiply the first term and multiply the second term. So if I was to go through and clean that up a little bit, my correct equation would be -2 times 3 to the x, then -1. And you guys will see that that equation that I just drew in orange matches up with my orange graph. Okay, why is that different now? I'm just going to circle it. It's because my graph, my base graph, is actually a transformed one. Keep in mind that our order of transformations always has to be a stretch or reflection first, which is my multiply, my add or subtract, my shift at the end. So every time that you've gone through and reflected a graph, there was never a plus or minus anything outside. It was always one term. Well, as soon as we allow a vertical shift to that function, now my function becomes more complex. It's multiple terms. I need to make sure that anything outside the function affects all terms. So now you say to yourself, well, then what do I do to that orange graph to get up to my blue graph? And we should be good that we can see that we would need to add 6 to the outside of our function. There is my shift up 6. So you guys can see the algebra on the right, but you can see why graphically on the left. Okay, your job now. Play around with some of these quirkier problems. Take a look at the other parts of question 13 and make sure that you're comfortable working through them. Okay, your job now, get some practice. Good luck.